Good morning. Thanks for joining this talk. Today, in this talk, we're going to take a look at some functional abstraction. The idea of next 20 minutes is to, we'll cover some core concept of functional programming first, and then we'll take a look at some functional abstraction to see how we can use it to solve our problems in a purely functional manner. So before we get started, note that I'll be using Scala Z 7.2.2 for the rest of the presentation. And let's get started. So if you take a look at functional programming, what's the core building block of functional programming? It's just functions. And somehow, perhaps that's the only abstraction you need to write a program in a modular and compositional way. Not a method, not a class, just a function. But when you refer to the term function, what do we mean by that? We mean the mathematical notion of total function. A mathematical notion of total function is defined as a mapping from a set of value of type A to a set of value of type B, such that each element from set A is associated with exactly one element in set B. So mathematically, A and B are also called domain and codomain respectively. So Scala, as a functional programming language, we use types to represent this domain and codomain. So you can think of a type as a competent description of a set of values. Using our functional paradigm of Scala, functions are nothing but just the values. So you can pass a function as an argument or return function as a result. And this notion is called higher order function. We can use higher order function to compose functions together in a compositional way. So in this case, I have a function from A to B, and I have another function G from B to C. We can compose this function together using and then combinator. And that's just one combinator, but perhaps you can use some other combinators as well to combine functions together. So in this manner, we can write code that are compositional, and we can do equational reasoning as well. So that brings us to the design philosophy that I'd like to cover in this talk, that we should always write total functions. So if you take a look at the example shown there, the read coordinate is a function that's taking some values from console and trying to convert it to double. So if I ask you this question that, okay, what's wrong with this function? Is it a function according to the definition we just had? If you take a look at the type signature of this function is from unit to coordinate. But if I take a look at this function, given that the string that we are reading and parsing it to double, if the string is not a valid double, then it will throw exception at runtime. So that's kind of insanity, right? Exception when it's thrown and it's not captured in the type signature. So following the type, I have no way of knowing that, okay, it might throw an exception. And also that it breaks referential transparency of functional programming paradigm. We'll take a look at this example later with the functional abstraction that we'll be explaining in the rest of the talk. But just to give you a simple example of the similar problem, we have a function divided by integer. So is it a total function? Absolutely not. For value 0, it might throw arithmetic exception at runtime. So how can we solve this and make it a total function? There are two ways that we can do that. The first way of doing it is to restrict our domain. So for instance, we are taking x as argument. We can come up with a new type called non-zero int, which restricts the domain further so that there is no value 0 in the domain. And we can use it as a total function now. And the second way of doing it is to use some other return type. For instance, here we're using option of double. So this type, option of double, as a codomain, represent the notion of optionality. That's one way of doing it in Scala, but you could use some other algebraic structures to capture the notion that this function divided by might not have an answer to your computation. So given x equals 0, it will return none. And for other value of x, it might give you the result of that computation. So this is how we can define an option. So note that here we are lifting a value a to a structure. So this notion can be further generalized for other kind of container types. So this container type will have a value A, but for instance, we can have a FA, which is a container type that can contain a value of A. So a typical example of it could be list, option. You could think of it as computation as well, that may hold or run forever, like task or future. So as soon as we start using this kind of abstraction in our function, the problem becomes that, okay, in order to apply a function to the value that container has, we need to first unwrap it, then apply the function, then wrap it back. It's kind of inconvenient, right? So these kind of containers, they often use this function called map, which allow you to apply a function to each element of the structure. So like in this example, we have option that has a map, list has a map, try also has a map. And this kind of parameterized type, this notion of map is not specific to optional list, but we can abstract this concept to a wide variety of parameterized types. And this idea is captured by this algebraic structure called functor. Functor abstracts the idea of mapping a function over each element of a structure. So in order for f to be a functor, it needs to implement this operation called map. But that's only part of the definition. The second part of the definition is that in order to be a functor, it needs to also satisfy some laws. So that's the cool thing about functional structure. It come up with a structure, and also it is associated with few laws. So typical example of functor is list. So we can think of the functor is a list. So if you take a look, it must satisfy at least these two properties. One is identity property, and the second one is composition property. The composition property refers to the fact that if we map f to the functor and then map g, the result should be equal to if we apply the composition function f of g to the functor. So anything, if we it has to be a functor, it must satisfy at least these two laws. If we consider set doesn't satisfy this compositionality law. I'll keep it as a homework for you guys to figure out why set is not a functor. Due to shortage of time, I'll just start explaining the other stuff that I have to say. So just to give you an example, here we have a binary tree, and we can create a functor for this abstraction quite easily. We have to use a map function. In case of leaf, we are trying to apply a function fa to b to it. And if it is a node, then we're traversing the left tree and the right subtree. So if we see it, this implementation, we can create any tree with a set of string, the tree that contains a string, and we can apply this function f to it and normalize the content of the tree of a string. So one thing to note here is that the functor that applies a function that only take one argument. But if we want to generalize this notion where we want to apply a function with multiple arguments, we need a bit more powerful abstraction, which is applicative. It's quite a powerful abstraction. The idea of applicative is to allow a function with number of arguments to be mapped. Unlike functor, which only allow a single argument to be mapped, applicative has this generalization. In order to be applicative, a functor must satisfy this. A functor must implement these two operations: apply and pure. So, what is, for instance, pure? Pure has the ability to convert any type A to a functor. So sometimes we refer to this operation as lifting. And apply has this power of applying a lifted function a to b to fa to produce fb. So using this mechanism, what we can do, let's take a look. There are three options, and we have this operation sum that's taking three integers and sum them up. So we can lift this function in applicative context first, and we can apply the function partially to the option that we had. And the interesting fact here is that we are partially applying the lifted function to a lifted value. So it gives some interesting observation from this thing is that we are applying function on arguments, but this argument may be a side effect. It may contain some kind of effect. So it generalizes some notion of programming with effects. So we started with the fact that we would like to generalize this application of function so that applicative allow applying function with multiple arguments to a structure, to a structure and elements of that structure. But somehow we ended up with a much more generalization there. A generalized view of applying pure function in effectful arguments. So that's the core essence of applicative there. So to sum up, we saw functor that allow mapping a function to each element of a structure. And we saw applicative, although the idea was to generalize mapping function with multiple arguments, there is more abstract view, that is programming with effect. But if you note, here we are only able to apply pure function in an effectful argument. But what if we want to apply a effectful function? Then we need a bit more powerful abstraction, and that is monad. Monad captures the similar notion of effectful programming as applicatives, but applicative style has some restriction that it only allows us to apply pure function, whereas monad generalizes the notion of composing function with effects. So in order to be a monad, it needs to implement a single operation called bind. Bind has the ability to extend a computation fa with the second argument there, from A to FB. So this is called bind and also flat map in Scala because the second argument there binds to the result of the first argument, fa. In case of the fact that fa fails, it propagates error throughout the chain. But if fa is successful, then it applies the function afb there. So user does not have to do the exception handling by itself. It's given by default by applicative, by this bind function. So to give you an example, recall we had this function read coordinate, which was reading some string and converting it to double longitude and latitude, and then it's creating this coordinate object. We can use this kind of case class IO to describe this computation. So in this example, we'll be showing that how we can refactor the previous effectful code to using monad to a pure function. So we can have this case class IO that can describe some unsafe operation. And we can describe the read line and print line function that we had in the previous function with this IO abstraction. So basically here, instead of doing the IO operation, immediately we are describing that what needs to be done. So we are describing computation as data. We can generalize this notion further with this polymorphic function IO, which takes any kind of computation and lifts it to the IO context. So we can define a monad for this IO. So in case of you're wondering, the point function, it's just lifting A into IO of A using the generic function that we have defined earlier. And the second function, bind, it's binding the first operation fa with the second argument f. So first it's invoking the first operation, and then if the operation is successful, then it's applying f and calling unsafe part from IO on the outcome of f. So it's chaining two operations together. In that way, we can chain a sequence of operation. Like first one is printing something and reading a line, and second one is printing latitude and reading a latitude value from the console, and returning an IO of string to string. So note that now we have a function signature from unit to IO string to string. At that point, we haven't done any IO. We just say that, okay, look, we can describe this IO operation, and we'll be executing it when we need to execute it. So we just describe the computation as data at that level. Now when we call this read IO function, dot unset perform IO, it will start executing the whole description, the chain. So this way, we can abstract side effects from our pure code and delaying the side effect as well. So given this way of chaining I/O operation, we can extend this example and read, for instance, latitude and longitude. What we're doing, we're reading it as double. We're trying to convert it to double, and if it fails, then we return none. If it's successful, then we're creating an option of that value. That's one way of solving this problem, but you could use some other abstraction as well, like either or something else. So we're reading latitude and longitude. We're not reading, we're basically describing that we like to read the longitude and latitude. And then we are combining them with the applicative builders there. So basically we have two options, and from the two options we're creating the coordinate object. And we're returning the coordinate object that we have created at that point. So in this example, what we did, we described several I/O operations that needs to be done. We haven't performed any I/O. But next, when you call unset perform I/O, it will start chaining those operations and start executing. So given you provided to the value longitude and latitude as a correct double, then it can convert it to coordinate object there. But it's written sum of coordinate. But given that you enter a wrong input there, it will provide you none. So now at the function signature, it's encoded that, okay, given anything, you will be getting an I/O of something, and I/O option or I/O of none there. So in this manner, you can isolate your side effect from your pure code. So you could have a pure code and impure code, and at the end of your call graph, there you are performing the side effect there. So just to recap, we had functor, we had applicative and monad. Applicative and monad is a bit interesting. It allows you to do effectful computation. So functional programming, we think of it as a lack of I/O, but that's not true. It allows you to do effectful computation with applicative and monad. It has the whole framework for you to write the happy flow, and the rest of the exception handling is done by this bind operation. But note that here we are only doing the structure preserving transformation. Basically, we are transforming FA to FB. What if you want to transform FA to something else? Then you need a complete different kind of structures that are monoid and friends. So I'll quickly go through them. A monoid is a mathematical concept which has only two properties. First one, that it has a zero element, and then it has an append function that can take two items of the same type and create one item from it. So it can reduce two items to one. So in this example, we have a monoid that append 4 and 6 and return 10 by combining them together. We can use this structure monoid in foldable to combine all the values of a structure into a single value. So it has this function called full map. It's more like this, that okay, you can map, it's more like making a sandwich, yeah. You can map a structure to monoid instance of it, and then you can reduce it. So you're mapping and folding. That's how the full map is defined. So you can see a monoid instance there. So that's there due to the fact that, okay, you might have something that is not reducible. So you are converting these objects to something that is a monoid. And when you have monoid, you immediately have this reduce function there. So you can reduce this thing to sandwiches. That's amazing, eh? So we can write much more generic function with this kind of structures. For instance, we can write a generic full map. The restriction here is that F has to be a foldable and A has to be monoid. Then almost every kind of structure, for every kind of structure, this foldable and monoid is defined for you, and then you can call this sum function. We can sum up a list of integer, a list of option, even a tree of option together. So this way you can derive much more generic implementation for your program, and the more generic your function is, there is a less chance that there could be a mistake there. The last structure that I'd like to cover today is traverse. It is quite interesting. Recall functor. Functor allow you to map a function f a to b, but traverse allow you to map a function a to gb. Basically, this f is a effective function. So Traverse is a functor, but it has much more additional capability. If you have a traverse implementation like that, then you can write almost any loop and apply this kind of effectful function on each element of the structure. And note that there is an applicative there, so applicative is there to do the effectful computation, handle failures. So this applicative machinery is there in Traverse to help you out in the case of failures. And another interesting property is sequence. So given that if you have f of g of a, you can get a g of f of a by applying this sequence function. It's like a future.sequence. I can give you an example. For instance, I have a list of option event, and I can convert it to option of list of integer by calling the sequence function. So using this kind of structure, we can create much more generic function. We can use those combinator to derive our program quite automatically. So the key takeaway from the talk, if there is any, always use first class function, or the total function, always use total function, and describe your computation as data. We have this misconception that FP functional programming doesn't have a way to handle effectful computation, but on the contrary, it has a framework for you given to handle effects. And as you use total function, as a side effect, you'll start using functional structure anyway. So given your domain model, if you use functional structure, much of the stuff you can derive automatically. Rather than writing every details by hand, you can get almost all the stuff free. Yeah, so that was basically it. Thanks for listening.